Hello students, welcome to EPG Pathshala. I am Dr. Aranya Bhattacharjee from the School of Physical Sciences, Jawaharlal Nehru University, New Delhi. Today we are going to discuss about a module, Motion of Electrons in Periodic Lattice Part 2 under the paper Solid State Physics. So students, let us see what we are going to learn in this module today. Learn about energy bands in terms of coupled equations. And what are these coupled equations? These coupled equations are derived from the Schrödinger equation in Fourier space. Learn about the energy band gap in terms of solutions of these equations. So these equations will generate some solutions, and these solutions would be the eigenvalues, and from these eigenvalues you can make out or derive the energy band gaps. Also learn about the effective mass of electrons in these periodic potentials. This effective mass concept I had already introduced earlier, but here we will give a very concrete definition about what exactly is the effective mass that we will learn, and also we will learn that how this effective mass changes sign. So it can be both positive and negative. Remember that, you see, the usual mass cannot be negative, but the effective mass can be negative. Also understand the concept of hole. So this concept of hole is important to understand how the electron transport takes place and how the band theory of solids is able to distinguish between metals, insulators and semiconductors. So in the previous module we had studied how the Bloch had developed the idea of motion of electrons in periodic potential of the ions in a solid. This idea gave birth to the Bloch theorem. It's a famous Bloch theorem which we studied for 1 dimension and 3 dimension. So this Bloch theorem, let me revise, is something to do with the periodicity of the potential. That is, a periodicity of the potential leads to the periodicity of the wave function of the electron. The electron in the Sommerfeld case, if you remember, is only a plane wave. In the Bloch theory, this is no longer a plane wave, it is modulated. It is modulated by the periodicity of the potential. So you have a plane wave multiplied by a certain function which is periodic, and this periodicity is exactly the same as that of the external potential. We had introduced the concept of energy band curves in the previous module. The effective velocities of electrons are found from the first derivatives of these energies, while the second derivative of these energies gives the effective mass of the electron. So you see that when we solve these equations that we're talking about, the Schrödinger equations in K space, the solutions are the energies, and from that energy we are able to derive the velocity of the electron as well as the effective mass. In this module we will now proceed further and learn about effective mass of electrons in the periodic potential. Also learn how the allowed energy states form energy bands and band gaps. So that, you see, the band gap basically means that the gap that exists between the different bands. This concept will help us to distinguish between metals, insulators and semiconductors. Energy bands. The Schrödinger equation in Fourier space in 1 dimensional, which was found in the previous module, is written as ek0 minus e phi k plus summation over the reciprocal lattice vector capital Q phi k minus capital Q, the uq is equal to 0, with ek naught is equal to h cross square k square by 2m, and capital Q are the reciprocal lattice vectors. The above equation represents a set of simultaneous linear equations that couple phi k q for all reciprocal lattice vectors. The consistency of these equations is determined if the determinant of phi k minus capital Q vanishes. Let us consider only one Fourier component of the potential UQ and write three coupled equations as the first equation E naught k minus q minus E phi k minus q plus U phi k is equal to 0. Second one is E naught k minus E phi of k plus U into phi of k minus q plus phi of k plus q is equal to 0. E naught k plus q minus E into phi k plus q plus U phi of k equal to 0, where mod of uq is equal to mod of u minus q is equal to u. That is, we have taken this. Note that here we have taken only three coupled equations, as k is coupled to only k plus q and k minus q. Actually, one can increase the number of coupled equations depending upon how many energy levels one needs. From the previous three coupled equation, the corresponding determinant is written as follows. Now, by equating the above determinant to 0 and solving for E, we get three roots of different energies for a certain value of k. Now, if we choose a different value of k that differs from the value in the first billion zone by a reciprocal lattice vector, say q, then no change occurs in the energy spectrum. The roots found according to the above procedure for a given value k are designated as E and k with n equal to 1, 2, 3. N is the band index. Thus, if E1k, E2k, E3k and others corresponds to the energies of the first, second, third and so on bands for a given value of k, the values E and k makes up the energy spectrum. By varying k over the allowed values and finding the corresponding roots, the full band structure can be determined. In three-dimensional case, k is direction dependent, and hence the band structure is also different in different directions. Energy band gap. Energy band gap is determined from the solutions of the equation that we had written down earlier, that is the Schrödinger equation in Fourier space, near the zone boundary. Always remember, the energy band gap is determined near the zone boundary. Consider for simplicity only two coupled equations, coupling phi k and phi k minus a. From equation that we had written down earlier, the Schrödinger equation in Fourier space, we have a solution of the form of this determinant, and we equate it to 0 to find the roots. Ek naught is equal to h cross square k square by 2m, and Ek naught k minus q as equal to h cross square divided by 2m into mod of k minus capital Q whole square. Solving this determinant, we get now the following expression for the roots, that is Ek plus minus. So the two roots are Ek plus and Ek minus is equal to half of Ek naught k minus q plus Ek plus minus square root of 1/4 of EKQ minus Ek square plus U square. Now the roots that we had obtained, that is Ek plus minus, are plotted in this following figure. As you can see from here that there are two distinct roots, one the lower one and the upper one. At k equal to 0.5, you have this band edge, that is the zone boundary. Of course, in the figure here it is says that it is k equal to 0.5, but actually if you look at our calculations, you will find that this edge is k equal to q by 2. This is 0.5 times the reciprocal lattice vector. Under such circumstances, the two roots, that is Ek plus and Ek minus, that we found reduces to h cross square capital Q square by 8m plus minus u. So that is, you have E plus as h cross square Q square by 8m plus u, and E minus is equal to h cross square q square by 8m minus u. And now if you subtract these two, that is E plus minus of E minus, you will get 2 times u, which is nothing but the band gap. That is the gap that exists between E plus and E minus. We now discuss the concept of holes. So before actually trying to understand the concept of effective mass, it is very important that we should understand what exactly holes are. So let us first understand the concept of holes. To do this, we take the help of this diagram of electronic energy bands. So as you can see from here that we have a valence band and we have a conduction band. So this valence band we see that lies below the x-axis and the conduction band lies above the x-axis. So this plotting of E and K versus the K vector. The lower band is the valence band and the upper band is the conduction band. An electron with wave number Ke in state A in the valence band is excited to state in the conduction band. This creates a hole at A with a wave vector Kh. Since the total momentum is completely in the filled band conserved, that is h cross summation over k equal to 0, then on excitation of an electron from the valence band to the conduction band, h cross summation over k minus ke is equal to minus h cross ke. On losing the electron with wave vector ke, the momentum of the valence band becomes minus h cross ke. This implies that the wave vector of the vacancy, that is which is called a hole, is now minus ke. An equivalent way of saying this is that we imagine a hole in state C with wave vector kh, which is the negative of ke, and so this also implies that the energy nk of this hole is the negative of the energy corresponding to that of the electron. So let us now discuss what exactly is an effective mass. Electrons under the influence of external electric fields are accelerated along the energy bands. In steady electric field E, the electron experiences a force equal to minus the electronic charge multiplied by the electric field E. The rate of change of the electron energy is dE by dt is equal to group velocity Vg dot F, the force, where the group velocity Vg is equal to 1 by h cross del of E and K. Also we have dE by dt is equal to 1 by h cross del of E dot h cross dk by dt. Now making an analysis of the previous equations that we have derived, the force then is written as h cross dk by dt. The acceleration of the electron is written as the rate of change of the group velocity, which is equal to 1 by h cross square double derivative of the energy E and K dot h cross dk by dt, which is equal to 1 by h cross square double derivative of the energy dot the force F. That is, this we have written down taking the help of the definition that we had for the force that we have found out, F is equal to h cross dk by dt. So rewriting the equation for the acceleration in terms of its component, we find that A of alpha is equal to 1 by h cross square summation over beta partial derivative, double partial derivative of the energy with respect to k alpha and k beta multiplied by f beta, where alpha beta is equal to x, y, z. That is, there any one of the three directions. Thus, from this definition of the acceleration, we obtain the inverse effective mass tensor. 1 divided by m alpha beta star is equal to 1 by h cross square double partial derivative of E and K with respect to K alpha and K beta. Here the star actually indicates it's an effective mass, not the pure mass, and it's a tensor because this effective mass also has got components and it varies in the three different directions x, y, and z. It is not necessarily the same. Since the energy E and K is in general not isotropic, acceleration will not in general be parallel to K. For isotropic energy surfaces, the effective mass is expressed as very simple 1 divided by m star is equal to 1 by h cross square double partial derivative of E and K with respect to K. So you see here that for isotropic energy surface is no longer a tensor and it's the same in all the three directions. So now if you look at this expression, a simple expression for the isotropic case, that is 1 by m star is equal to 1 divided by h cross double partial derivative of the E and K with respect to K, we find that this can actually take both positive and negative signs. So this is positive near the bottom of the band, that is d square E and K by dk square is more than 0, and it is negative near the top of the band, that is this double derivative of the energy E and K with respect to K is less than 0. Instead of thinking of these electrons as having negative mass, one can think of them as being holes with positive charge. So based on what we have learned up till now, we can now try to make an analysis as to how metals, semiconductors and insulators differ from each other. The transport of electrons in solid is dependent on their band structure. Once the band structure is known, it is then possible to predict whether the solid is a good or a bad conductor. Now, if there are n number of primitive cells in a crystal, then the number of energy states in a given band is equal to n. Each state can accommodate 2 electrons of opposite spins. Hence, in order to fill the band completely, 2n electrons are required. A band would be completely filled if a primitive cell contributes to an even number of electrons to the bands. Let us take an example and consider a monoatomic crystal in which each atom has a 1 valence electron. Now, for the band to be completely occupied, 2 atoms per primitive cell are needed. Similarly, if there are 2 valence electrons per atom, only 1 atom in the primitive cell is required to fully fill the band. From this we understand that in solids, if one or more bands are completely filled and all the others are empty, then that solid will behave like an insulator at 0 Kelvin. Typical example is of diamond. The carbon atom of diamond have the electronic configuration 1s2, 2s2, 2p2. The mixing of 2s and 2p wave functions results in the sp3 hybridization. Each of the 2 hybrid s and p subbands can accommodate 4 electrons, which fill the lower subband, leaving the upper one vacant. The band gap is about 5 electron volts. These characteristics tells us that diamond is an insulator. In insulators, the energy gap is greater than 5 electron volts and electrons have to be excited to generate electron conduction. Usually, the applied electric fields are not large enough to provide this kind of excitation. So you see that we have already discussed about insulators, and these insulators, as we see, that have energy gaps equal to or more than 5 electron volts. Now what happens when the energy gap is lower and is about 1 electron volts? Is smaller than 5 electrons, so naturally one would expect that it is not an insulator, but it is not a conductor either, somewhere intermediate. So the solids show conductivity which is intermediate to that of insulators and metals. So these solids are classified as semiconductors. That is, the classification is based on the very simple fact that energy gap, which is so important. The energy gap is less than that of the insulator, but more than that of the conductor. So you see that energy gaps are derived from where? The band energies. And the band energies were derived, their solutions of the Schrödinger equation in K-space. So in semiconductors, like insulators, the valence band is completely filled. The difference lies in the band gap. The semiconductors are of two types, namely intrinsic and extrinsic. So what is intrinsic? Intrinsic means semiconductors which are pure, monatomic or diatomic solids. The extrinsic semiconductors are made from the intrinsic ones, materials, by adding trace amount, very small amounts of suitable impurities to enhance the level of the charge carrier density. So you see that in order to generate a finite conductivity in the intrinsic materials, we add a certain amount, a very minute quantity of trace amounts of a suitable impurity. Now this suitable impurity then has to be chosen in such a manner what we want, whether we want to have excess of holes as charge carriers or we want to have electrons as charge carriers. Examples of semiconductor materials are silicon, germanium, gallium arsenide, indium SB. All these are examples of semiconductors which we have. Now let us discuss the case when the number of valence electrons per primitive cell is an odd number. So you see in the earlier cases which where we were discussing about even number of electrons per primitive cell, but now let us say that we have got odd number. In such a situation, the topmost occupied band is partially filled because it's odd. And why are they partially filled? Because you see, you have now one unpaired electron. It's odd, that's why. And hence these solids exhibit electrical conduction on the application of an electric field. Such materials are called metals, and they are good conductors of electricity. Alkali metals contribute one valence electron per primitive cell, and as a result the highest occupied band is only half filled. The electronic configuration of sodium atom is 1s2, 2p2, 2p6 and 3s1. Okay, this is an example that we are taking for our metals. The 10 electrons in the closed inner shell form the filled narrow bands. The lone outermost 3s1 electron produces the half-filled band that is responsible for the metallic behavior of sodium. You see, the one electron in the 3s level, it's a half-filled band. If you just put in one more electron, it will completely fill, and that would make sodium an insulator. But that does not happen because you have only one electron in the outermost shell. So students, let us summarize what we learned in this module. We learned first that how energy bands and energy gaps are formed. So let me recollect. So these energy bands are formed by the solutions of the Schrödinger equation in K-space. From these energy bands, we found out the energy band gaps, that is the gaps that exist between the different energy bands. Then we learned about the concept of holes. We learned also the concept of effective mass. How? The second derivative of the solutions of the Schrödinger equation in K-space. The difference also, we learned how metals, semiconductors and insulators that we have based on the band theory of solids. Thank you.